Good morning, good afternoon, good evening, wherever you may be. Welcome to StarWind Software Webinars. I'm Max Kalametsev, your host for today's event. And our idea today is to get unbelievable performance without expensive old flash arrays for your virtualization environment. And before we start the event, I would like to do some housekeeping as well as check with our audience to make sure everyone's getting good audio and video quality before we start the event. So please let me know through the GoToMeeting questions and answers or GoToMeeting chat window by confirming you see the screen and you hear the audio. Okay, excellent. So this means you already know how to use the GoToMeeting control panel, and questions and answers box is the place where you should go to submit any of your questions throughout the webinar. And in the end, we'll have a Q&A session where I'll answer all of these questions as good as I can. And also, we are recording this session. I will put it on YouTube later as soon as we convert it. So I think it will be on our channel tomorrow. And now, thanks for the feedback, and let's begin. So a quick agenda for our today's event. First, we'll look how virtualization worked good for the servers, but introduced some troubles for the storage. Then we'll learn about Blender and what is it, why is it so bad for your virtualization environment, and especially for your storage. And then we'll see how we could overcome Blender, and of course how we can eliminate Blender. And in the end, we'll have a questions and answers session where I'll answer all your questions. Right. So virtualization, virtue for the servers, troublemaker for the storage. And let's see what we had without virtualization. Obviously, we had one server and one application on it. Sometimes two applications, but that was not so often. And the idea was that every particular application tried to optimize the way it uses the drives, tried to lessen the number of random writes to the disks, knowing that any random write or random I/O to the storage degrades performance. So they tried to use cache, use internal buffering and all that stuff to make sure they're using disk with maximum efficiency and getting the most performance from it. And that was good. The downsides of non-virtualized environments were, of course, no effective resources utilization, no effective storage management, and complex management overall, where you had, let's say, 20 applications in your office, especially clustered. That would mean that that's at least 40 servers and maybe a SAN. So that's a lot to manage just physically. If something fails, it can become a nightmare. So with virtualization kicking in, some stuff became much better. One server, we were running multiple applications on it. We've got effective compute resources utilization. Our servers are now utilized up to 99%. And you may have seen this article on the web saying that every fourth server in the world is just sitting doing nothing, and that's true. Without virtualization, they were sitting doing nothing, and 3 of the servers are working with virtualization, so they're actually working, and 4th server is still with that system administrator who says, okay, I will not virtualize my applications, I'm okay this way, this is more reliable, etc. No, actually it's not true. Virtualization really does its job, it does it really good, and it comes in a variety of flavors. But I digress. And effective storage management is one more thing about virtualization. So if you have local storage on your hypervisor, you can manage it much more effectively with multiple applications running on it. And of course, you get simple management because you simply remote into, let's say, Hyper-V Manager or vSphere console, and you see all your environment. You can configure networking internally without going to those cables and switches and even going to the data center. You can be sitting on the beach and managing your data center. That's absolutely awesome. But there was one big problem which appeared with virtualization, and it was a big hit on the storage with deploying multiple applications. Even though every particular application would optimize its load, together they produce an effect called IO blender. So let's take a closer look at it and what it is, how it appears. So the virtual machines on the right, on top right, produce some load. They want to write some data on our storage. And we have these blocks A1, B1, etc. So these blocks are processed by the hypervisor and then sent to the storage. Well, each particular VM may be optimizing its load on the disk and trying, let's say, write sequential only. If you have two of these VMs, it's more or less okay. In a typical environment, we have at least 10 to 15 virtual machines running on one virtualization host. That means that we have a perfect mess of I/O across all our drives. And with standard file systems like NTFS or BerkeleyFS, where we have pre-allocated place for every block on the disk, that means 100% random write. And be it small blocks like 4 kilobyte or large blocks, even 256 kilobyte, you still get a terrible performance degradation. So overall, this effect is called IO blender. And it works for any spindle-based storage, and it kills both performance and latency, of course, and all those warnings you get from the hypervisor are often caused by just too much load put on the spindle-based storage. And of course, the actual problem people are experiencing, they don't know what a IO blender is or what latency is. They just know that their applications are not working as supposed. They're simply slow. And that is a real issue we are trying to fight. So there are ways to overcome IO Blender, some of them. First of them is deploying one RAID group per typical load. So let's say you have a SQL base, it has a separate set of drives. You have a file server, it has a separate set of drives. And then you have other servers with separate set of drives. But the downside is you need too many drives for that, and it's kind of a management nightmare from the storage perspective, because having all those islands of storage segregated doesn't do you any good. You cannot effectively utilize your storage. So you have one server utilizing half of the provisioned space, and then one server maxing out the available storage for its typical load, but you cannot really move a few gigabytes from one group to the other. So they're completely segregated. Another solution which a lot of people are doing right now is deploying all-flash storage. That's definitely a killer. It works perfectly. All-flash storage doesn't care about IO Blender. So the solid-state drives do not know what seek time is, and they do not know what is increase of latency. They simply work and process. It's like working with RAM. It's extremely fast, and it doesn't care about random or sequential operations, as well as it doesn't care about block size. So that's a good solution. The only downside is it's extremely expensive and it's not really long living. So all SSDs tend to burn out under load after a few years. Some internal tests, we managed to burn several of them in something like 3 weeks, and those were upper grade consumer SSDs. Enterprise SSDs will last longer, but to give you an idea of time, average lifespan of the SSD, that would be it. And the final idea is to implement storage with VM-centric file system. So the storage should be actually aware of what's happening on top and kind of adapt to the load produced by the virtual machines. And there are several techniques, and there are multiple vendors doing this. You may be familiar with words waffle or castle from companies NetApp and Nimble. So these companies have been fighting IO Blender for quite a long time already. There are also some implementations in the software level, and some vendors are doing log structuring and acceleration on the software level. But let's give you some more details of how we can not only overcome but eliminate IO Blender with our solution. So the idea behind StarWind's virtual SAN log structured file system is pretty simple. So I've described it as 1, 2, 3, 4. So first we buffer the IO stream in RAM. Since we're working natively on the hypervisor, everything happens within the same box. You don't think about a hypervisor and the dedicated SAN. Then all these small random writes coming from the virtual machines are gathered into one big block of data. So let's say you had 4 kilobyte writes, we pack it together and form a 16 meg block, and these blocks are then written to the storage sequentially. So we do not actually care if the block had a particular place on the disk previously. No, we write everything sequentially. We maintain a log of our write operations in server's RAM, and this way we eliminate IO Blender. So effectively, we just started utilizing our spindles, all sequential as tape. You simply write to it and you don't select specific places. So you can easily write massive amounts of data really fast. But you may be wondering, what about reads? How can we improve reads in this case? Because in this case, reads become full random. And the idea is really simple. We utilize Flash to accelerate reads. This way, we do not wear out Flash with constant writes. Flash has no seek time, so it doesn't decrease performance when we do any type of random read. And also, we read with big blocks, so we eliminate spot burns on the SSDs. So together, by intelligently combining spindles and Flash, we accelerate both loads. And there are actually a bit more specific details to LSFS, and I would say some miracles some storage admins wouldn't believe. So let's do a little impress me slide. First of all, most of virtualization admins will say, I will never use RAID 5 for my virtual machines. And I'll be with them. I agree with that, up to the point where we come to the log structured file system. With log structured file system, RAID 5 works better than RAID 10. It provides better space per drive ratio, so you have more usable space on your storage. And we only use it sequentially, so the impact, the so-called RAID penalty, is not felt with the log structured file system. Another miracle would be nearline SAS, or let's call it SATA RAID, shows more IOPS than 10K SAS RAID in a traditional system. So with writing everything sequentially, we are not looking at the storage IOPS anymore. We know that, let's say, standard SATA drive or nearline SAS drive produces about 70 IOPS if we put random load on it. But if we put sequential load on it and write with big blocks only, then we can get 90 megs a second. And 90 megs a second is already something close to 20,000 IOPS. So compare number 70 we had with the traditional file system layout, and 20,000 we have with writing on the disk sequentially. Then no spot burns on the flash storage and longer lifespan of flash storage in a production environment on the first level of your storage, on the tier 1 storage array. This is achieved by using flash for its good qualities and trying to compensate its lifespan by writing less to it, instead reading a lot from it. We can always write fast to our spindle since we write sequentially. We don't need to write to flash at this point, so we can read from it. You can, of course, use flash for reads and writes as well, but the whole idea is to use less flash, more spindles, and get effective storage utilization and effective flash utilization. So it's a winning combination. Then, as LSFS combines small blocks into big ones, it does support snapshots natively. So snapshots are not causing any performance penalty. We simply use redirect on write, which would be a slow operation with traditional storage because you have to stop writing in one place and then start writing in the other place. And you have a snapshot file on your disk, and then you have your actual data file on your disk. With log structured file system, remember, we're only writing sequentially. So at some point we just put a checkbox saying, okay, up to here we have a snapshot, and continue writing. And everything before that checkbox is a snapshot. Everything after that checkbox is your new data. Should anything happen, you can always revert to all those points in time, and technically you can revert to any second of your array's life. And of course, we have the write log in RAM. So why not use it more effectively? We implemented inline deduplication without any extra overhead. We already have our RAM, we already have our write log, so we can work with that write log, check for the duplicate blocks and remove these duplicate blocks on the actual disk and just have symbolic links for it. So inline dedup with no disk effect and no performance impact is also the part of the log structured file system. So essentially this is the way how StarWind is able to achieve excellent performance without all flash storage underneath. And what would be the typical use cases for the log structured file system? First of all, it's virtualization, any type of virtualization where multiple applications are writing to the same storage array and produce a lot of random I/O. This is good use case. Then any write-intensive environments, let's say high performance computing where you need to write massive amounts of data to the storage and then process it, like databases, let's say, are also really good candidates for the log structured file system. And of course VDI, because VDI is mostly writes, so the I/O distribution in VDI environments is 80% writes and 20% reads typically. And if 80% of our data is written sequentially by means of LSFS, we can be completely calm and relaxed about good performance we get with it. And don't forget we have deduplication built in on top, so all your virtual desktops are automatically deduplicated. So 100 virtual machines will actually occupy the space, let's say, of 20 if we take into account the page files, the swap files, and the actual user data residing on these virtual desktops. And with that, I would like to thank everyone for viewing the presentation. I know I have raised a lot of questions, so we're starting the questions and answers session right now. So just give me one moment. Let me open the questions and answers panel and I'll go through your questions. Okay, so question from one of our attendees. What are the base memory requirements for testing this solution? StarWind's LSFS requires at least 3.6 gigabytes of RAM per terabyte of stored data. And on top of that, you can also put write cache from RAM. So let's say 4.6 gigabytes for 1 terabyte. That would be the base requirement. Next question is this available now? Yes, it is available now. It is already available in StarWind Virtual SEN. And here is question was, okay, a practical question here. Already have an array with a mix of drives, some 10K SAS and some 7K SAS. Would the 7K drives be okay with LSFS? Also, I have 2 SSDs. Can I use them for cache/speed? Indeed. So the idea behind LSFS is to use high capacity, low speed drives for storage. And you may also be wondering, are there any trade-offs for using LSFS? And there is one tiny trade-off. It uses 3 times more space if you put 100% random load on it. And that's something synthetic. In reality, it can grow 2 times, but the idea is we use high capacity, low speed drives. So even with 10 times storage over provisioning, we wouldn't get more expensive than by going all flash or by going with standard 10K or 15K SAS. The SSDs, of course, can be used for the level 2 caching. Examples of log-structured file system. Question from our attendees. So as I already mentioned, 2 most known examples would be NetApp Waffle and Nimble Castle. The difference between StarWind's implementation of the log-structured file system and the one from these companies is that StarWind provides fully software log structuring and doesn't rely on any proprietary hardware, while both NetApp and Nimble are hardware-only solutions, and so far there is no way to get, let's say, Nimble software or NetApp software on your production virtualization environment. Okay, question from our attendee, is compression available? If so, does it hurt speed of read-write or deduplication? Compression is not yet available. We're working on that, and since we're doing deduplication, compression may not have such big performance impact on the environment. So this is still something to be discussed since the feature is not yet production ready. It's only in our lab. And one more question from our attendees. Is this compatible with both VMware and Hyper-V? Indeed, it is available for both VMware and Hyper-V environments. In fact, you can also use it for Xen environment. You can use it for any non-virtualized environment as well. So it technically works for any hypervisor. At the front end, you still see, with VMware, you still see a VMFS partition, and with Hyper-V, you still see an NTFS partition or ReFS partition. So there is nothing proprietary we're presenting at the front end. And a question from our attendees, is LSFS really production ready? Yeah, a lot of people ask this question on the forum. I would say it is production ready. Previously, there were issues where we provided minimal recommendations for LSFS, and a lot of people were overusing it and not following the deployment best practices for it. And with file systems like that, it is really important to do. That's why you do not see a lot of deployments like this by other vendors, because if you follow the guidelines, you're okay and everything works smoothly. But if you do not follow the guidelines, the storage starts acting up real quick, and that caused a lot of questions on our public forums as well as on the web. Okay, let's see, any okay, here's one. I have a 16 gigabit fiber channel SAN with 24 4 TB SAS drives in RAID 6. This doesn't work well with random I/O. Can I use this and StarWind to increase the performance of my current SAN? Indeed, you can use it with your current SAN. In this case, StarWind will be installed in your hypervisor. It will take ownership of the fiber channel LUNs and then present them to the upper application or virtualization layer as log-structured storage. So 24 for 96 minus 8, so it will be something like 30 terabyte of usable high performance storage for your application environment. Okay, one more question. How does this compare with the Quantum DXi products? I'm not sure. This is something I would actually gladly answer once I read through the Quantum offerings and see more about their solution. I'll be really glad to help. So if you have some time to discuss it, I would be glad to answer that question via email after the webinar. And here is one I wanted to read. Guys, how the hell is SQL dominantly writing and how VDI writes 80% and 80% writes and sequential? You said that in your presentation. So I'm wondering, where is your data from, because I like to live in that world. Okay, so SQL is not dominantly writing. That may have been a mistake from my side. There are multiple workloads SQL can generate, and depending on the base or log file you're using, the load is different, but the idea remains the same, that it is doing random I/O as well. And with VDI, 80% writes and sequential, the idea was to have 80% writes going to the log structured file system, thus they become sequential. Normally 80 to 90% writes are random in case of VDI. So this is the documents I've got on the web, and I've read this on Login BSI. I also had some information from Dell, and I do not remember the other sources I got the information from. But the general idea is you do not really care about random I/O if you know that your storage anyway turns it into sequential I/O. Okay, I think that was all for the questions, and I would like to thank everyone for attending our today's event. I know we could go a bit more deeper, but I tried to keep it less techy and more of a presentation showing which problems we actually solve rather than going deeply technical. So we also have a tap room, which is our every Thursday event with more technical details and also some live demonstrations. So I definitely invite you to sign it up for it. and my colleague will get a bit more in depth about the log structured file system and how it works. Thank you everyone, and bye bye.